All right, this is 2011 Form B, problem number 3. This is a weird year. There were only 2 calculator problems. So number 3 was a no calculator problem. And it gives a graph and some functions. They give you a root function squared of x, shown from 0 to 4. And then they give you a line function, g of x, from 4 to 6. And they define R as the region below those 2 curves. They give us all the points of intersection. 4, 2, where the 2 curves intersect, 0 and 6. All right? And then it asks you to find the region of R. Okay? The area of R is simply the integral, right, of f of x from 0 to 4 and g of x from 4 to 6. That integrant, which would be this integrant, is worth a point. All right? Which is just replacing the signs with this stuff. This is sound weird. All right, so again, right here is f of x, the integral, the area under this curve from here to here. So that's that section. This is the area under that curve, all right? When we do this integral, all right, when we do this integral, integrating x to the half power, change a radical to the exponent, add 1, becomes 3/2, divide by 3/2 from 0 to 4, the evaluation. Now over here, there's 2 ways to do this problem. You could do the integral of 6 minus x. Exactly. You could look back up here. You guys see the triangle? 2 by 2. 1/2 of 2 by 2 is just 2. I would be tempted to write this as the integral and then just go plus 2. Because I know it's a triangle. So I'm not even going to figure that out. I am going to rewrite this as 2/3 x to the 3/2, 0 to 4. All right. And this is 16/3, right? Because it's going to be 16/3 minus 0, do you agree? Plus 2. And I get an answer of 22/3 then. The answer is a point. The antiderivative right here is a point. And the original integral is a point. 3 points. All right. So we'll pause this and we'll group it and get ready for problem B, part B. Part B says the region R is the face of a solid for each y from 0 to 2. So we're on the y-axis, guys, from 0 to 2. The cross-section of the solid perpendicular to the y-axis is a rectangle whose base lies in the region R. All right. There's a rectangle, and its base is right here. That is the base of the rectangle. All right? And its height is 2y. Okay? So if I draw this rectangle, I start by drawing the rectangle. You guys agree this is 2y? And I'm going to call this length L. You see how this attaches to the graph. So the rectangles are coming up. You guys want to visualize this shape. This is the front rectangle, and these are all rectangles going back. This shape right here is this shape right here. And they're all rectangles then on the faces. We don't have to visualize it. It helps to see it. We know based on what it said, and that it's perpendicular to the y-axis, that is L. We have to catch then that we're going to have to solve both of these functions for x. Right? So we're going to have to start there. All right? So if I solve both of these for x, y equals square root of x, so that becomes y squared equals x, right? And on the other one, we had y equals 6 minus x, so x equals 6 minus y. I just solved those 2 equations for y, because I need those functions. And it says, write but do not evaluate the integral, right? Which is going to make this a lot easier. We know, since we were evaluating about the y-axis, that it has to be dy. All right? And if I do this now, we're going to have to define L. L is the x distance. It's going to be g of x, which is this one. We have to figure out L, all right? L is going to be this x minus this x. So it's going to be 6 minus y minus y squared. You guys see how I got that width? And they said the height's 2y. So now, area of y. What is AY? AY is simply the area of a rectangle. It's just this times that. So our integral is just 0 to 2 of 2y times 6 minus y squared dy. The integrant and the answer. This is 3 points. It says the integrant is worth 2 points, which would be this, and the whole answer is worth a point. I don't know how you would screw up getting the limit 0 to 2 in dy. It's really coming to this. You have to visualize that rectangle. Do you catch the English? The hardest part here is this right here. You have to read this and get this picture. You guys got to start drawing the shapes. I saw I think I saw a rectangle on yours. You got to start drawing the rectangles. All right, let's pause this and get C ready. All right. There's a point P on the graph of F at which the line tangent to the graph of F is perpendicular to the graph of G. How about that for a multiple, right? Find the coordinates of point P. There is a point P on the graph of F.
Bring out P to the office, please. Bring out P to the office.
Someplace there is a P, all right? At which the tangent line to the graph, at which the line tangent to the graph of F is perpendicular to that of G.
We know this.
So this line,
the slope of G is -1. So
we know these are perpendicular. You know the slope of G of X is -1. You guys agree?
So then is this one of those?
Okay, what do we know about perpendicular lines?
90 degrees.
And 90 degrees. We know the slopes are opposite reciprocals. So don't you guys agree we can immediately write this?
Yes.
I gotta believe this is a point. It is not. This is not a point, but we're going to have to get this. F prime of x is going to have to be 1. We're going to need it. It's not a point. I need f prime of x. Well, that's pretty easy. Let's take the derivative of this. Do you guys agree? The derivative of square root of x. Do you guys agree that's 1 over 2 square root of x? 1/2 x to the -1/2. This is a point, looking at the score sheet. This is a point. Now, Luke, I'll pick on you, because you know what? You had the equation written, but you never wrote this. You used this part of it, but you didn't write this statement. So guess what?
No point for me.
No points for you.
Does that mean if
You don't write this, you won't get the point. What Luke wrote was this. Luke made a mistake, and he used the wrong number here. Because he knew that this had to equal f prime of x. So you put the value you had there.
Would they pull one of those things where if you don't have that written, all subsequent,
Well, who knows? But the point is we always write the derivative. So here we go. We got to solve this. If I solve this, do you guys agree it's multiply by that? So 1 equals 2 square root of x. 1/2 equals square root of x. Square both sides. X is 1/4. So this is the equation. This is the derivative. These are each one of those are a point, okay? I solve for x. I get x is a 4th. I plug a 4th in and make sure it works, right? Because when I square stuff, bad things can happen. It works. I checked it. How do I find point P then? If I know the first point is 1/4, I just got to take it back into the original function, which is what is the square root of 1/4? Plus or minus 1/2. Look at your graph.
Minus goes away.
Yeah. Look at our graph. There is no minus. It is plus or minus 1/2, but we know to ignore the negative because the curve is in the first quadrant. So there's point P, and the coordinates of P is a point. I think B is completely achievable. You guys got to start looking through AP problems and finding the ones that don't have discs or rings. We have to start. We want to get these rectangle problems. We don't want to miss these. All right. And that is 2011, problem 3, no calculator, Form B.